Okay, so good morning, everyone. Let's get started. The topic for our lecture today is trajectory generation, part one, waypoint. So in this lecture, I'm going to introduce you this a method that we can generate trajectory, but I will start with a very simple way, so you can have some idea. Um, So before we start, let me briefly show you the content for today's lecture. So I will start with the review of kinematics of Omni wheel and Mecanum wheel robot. Then uh, you will be learning velocity transformation and acceleration transformation. Then we can start the trajectory generation. So first, let me give a brief review on kinematics of Mecanum wheel and Omni wheel robot. So let me start with the schematic of a robot. So let's say we have a robot in this configuration, in this orientation of different color. So the robot itself has its own axis, its own frame. It's called body frame, HB and YB. So, and the environment frame, which is fixed and it's called global frame. Okay, frame H and Y. And here is the origin of the robot. It's denoted by like OB. And so the kinematic is the relationship between the velocity of the robot in the body frame and the angular velocity of each wheel. Okay? So each wheel has angular velocity phi dot. So for let's say yeah for convention that I choose is that this wheel is number one, this wheel is number two, number three, and number four like this. So this one is supposed to be angular velocity of wheel number two. Okay. Um, so the relationship between phi one dot, okay, dot up to phi four dot and h dot, okay, hb dot, yb dot, and psi dot. So where psi? Psi is the angle between the x-axis of global frame and the body frame. Okay. So kinematic is the relationship between this group and this group. Okay, called kinematic. So I just say relationship. Okay, and the relationship is defined by the equations like this. We have phi, so phi dot uh, that contain all phi one dot, phi two dot, up to phi four dot. Okay, equal to a matrix J times HB dot YB dot and psi dot. Okay. And matrix J is constant. So we have element J11 here, J12 here. Okay, it's like that. So this matrix J has four rows for the four-wheel robot. Okay, 4 by 3. And J is constant. Well, and so for this one is called inverse kinematic. Okay. Then if we want to find forward kinematics, we define this term. So I denote by compact form, phi dot equal to j times h dot hb dot. Okay, capital H represent this vector. And then for the forward kinematic, we need to find hb dot equal to j dagger time phi dot, where j dagger is, yeah, j transpose times j inverse times j transpose. Okay, because j is not square. Okay, and the next part that I'm going to explain is about transformation of the velocity vector in the body frame to the global frame. So let me draw it again. So we have body frames like this. Okay, and the vector of velocity, okay, velocity vector hb dot is here. It means it has component on this one, this, and on component on y like this, and also component for the psi dot like on the z-axis actually. Okay, on the z-axis like this. That is hb. And now we want to transform this vector into global frame, which means okay, I want to find this component, this component on the x-axis, and then I want to find this component on the y-axis, yeah, y global, x global, right? So I need to transform it using rotation matrix. Yeah, also the vector of angular velocity psi dot on the z-axis, I also need to transform into the z-axis. So first it stay in the zb. Okay, so actually because z and zb are coincided, so the transformation from zb to z will be still the same. Okay, so I have h dot b like this. Now I want to transform into h dot in the global frame, right? I mean, h has component a capital H dot has component this one. We can call it like vh, and for this component we can call it vy, and then we have psi dot. So here I just multiply it by rotation matrix. Okay, I can transform this coordinate. And if I want to transform from global frame to body frame, and so I can have hb dot equal to, can you give me the answer, Subun? Inverse of R. Can I simplify a little bit more? Yeah, so I can just use transport. Okay, and yeah, actually, so this point already cover this part. I delete this one, and then acceleration transformation. Well, um, why do I need to? Okay, so yeah, I will start from this and uh, come to this point that why we need to find time derivative of rotation matrix. So we have h dot equal to rotation matrix time h b dot, yeah, h dot b. Then I want to find acceleration matrix. Okay, h double dot equal to r dot psi times hb dot, oh sorry, yeah, correct, and then plus r psi times h double dot b, right? um, well, okay, so and here we need to define time derivative of rotation matrix, and at this part I'm going to explain the general formulation for rotation matrix that you can use for other type of robot or even aerospace vehicle. So this is very useful. So I'm going to explain today. Um, okay, so time derivative of rotation matrix. Uh, okay, so I start from here. What we have learned before that R transpose R equal to identity. Then if I take the time derivative or the transpose R plus R or transpose R dot equal to 0. So we can say that R dot transpose R equal to, no, I should write this, R transpose R dot equal to minus R dot transpose R. So can I rewrite like this? Uh, Minus R dot R, oh sorry, R transpose R dot and R transpose. Is that okay? When we drop the transpose to each one, we need to change the order. So from this to this, we just drop the transpose, right? So what does this tell you now? If I take omega, if I let omega equal to R transpose R dot, then omega actually, then omega equal to minus omega transpose, which means which means omega is skew symmetric, right? And then, oh, well, sorry, I think this one I need to use omega prime, but I will explain later. This one should be omega prime, omega prime. And similarly, I can use R transpose equal to I, and then time derivative R transpose plus R dot transpose equal to 0, and I can have R transpose equal to minus R dot transpose or minus R transpose all transpose, and let omega equal to R transpose. Then omega is also skew symmetric. Okay. So here I have two relationship. I have R transpose equal to omega, and I have R the R transpose R dot equal to omega prime, right? So I can write like this: R dot equal to omega times R, and R dot equal to R times omega prime. Okay, and these two, so it means omega R equal to R omega prime. Something tells you now. Omega and omega prime somehow must be related, right? So I can write omega equal to R times omega prime times R transpose. Okay. Um, yeah, actually, I need to prove one more identity in order to conclude omega, the relationship between omega and omega prime. Um, so yeah, in order to prove that, let me try. Okay, I need to prove one identity. Yeah, well, what we know so far, this one is skew symmetric. This one also skew symmetric. Okay, maybe like this. This one skew. This one also skew. Okay, so let me um, give you the relationship between A cross B. A, we have A here, we will have B here. So A cross B here, C equal to A cross B. Um, let's say all of them are okay. I can write prime, then C prime, A prime, B prime. Okay, so All these vectors are measured in body frame, okay? In body frame, in body frame. Um, so in order to transform all of them into the global frame, so I apply rotation matrix to the whole system here. So RC prime equal to R times A cross B. Okay. So and here I have, oh sorry, prime, right? Prime. So and here I have A R prime cross E prime. It means I can have, yeah, so I can have R times A, oh sorry, no. Yeah, I can write like this. A prime cross times R times B prime. Okay. And here actually, what can I write here? Oh, sorry. Okay. What can I write here is that actually here is A cross B because where R uh, yeah, what I'm trying to say is that after we transform B prime and A prime into global prime, then the cross product between A and B must equal to C, right? So here is A cross B. Um, okay, so here I have A cross times B. Uh, something is missing. Something is missing. If something is missing, I should have another or transpose. No, R times C prime should be C, and C is actually, this one is C, yeah. And what if I have this? I can have B here. No, something is missing. So sorry. Um, is this correct? This one. Ah, this one is like this. This one is like this. Actually, I made a mistake here, and actually, there is a mistake here. Actually, here I can have rotation matrix, and I split like this. A cross is a skew symmetric matrix, and then I have a B prime here. Is that okay? Yeah. Actually, this one, if we want to write like this, A prime and then cross like this, you must have R and then B prime here, right? If cross is here, but now I still keep this one like this. Okay, and then I have R A prime cross and B prime here. I can write R transpose B. Yeah, this is what I want to say. You got it? R transpose B is B prime. So we have A cross here equal to this is A cross B equal to all of this and then times B as well, which means okay, I mean like this, which means A cross equal to R times A prime cross times R transpose, right? So what does this tell you? This tells you that because A cross is skew symmetric, skew symmetric. This one also skew symmetric. Okay. This tells you that if you have a skew symmetric matrix from a vector in the body frame, and then you transform by multiplying or from the left hand side and or transform from the right hand side, then you have skew symmetric of that vector in the body in the global frame, right? So you can see the relationship between A prime and A here. This means these two are the same vector. It just one is measured in body frame and another one is measured in global frame. So as you can see here, omega and omega prime are actually the same vector, but omega prime is measured in body frame. Omega is measured in global frame. So that actually omega is just angular velocity cross, same vector, right? Then we come back to here. We get it back to here. We can have omega is omega cross and omega prime is omega prime cross. Okay. Then we get back to here. We can have actually this one is what is this? Yeah. So here actually omega cross R and this one actually R times omega prime cross. Okay, so this is the definition of time derivative of rotation matrix. um, then all right, why all these are important? Well, come back to this point. Yeah, come back to this point. For the acceleration equation, we can rewrite h double dot equal to, because this one is omega cross r, hb dot plus r h dot double dot b. Okay, and if you like, you may write this one um, as h dot right here. So this one is just omega cross h dot h dot plus r h double dot b. So sometimes you can you see a many times you can see that if you have a vector, let's say you have a vector in the body in the global frame, okay, global frame, and you want to find time derivative of this vector, you just write down okay, well let's say this one equal to j omega dot, for example, j omega, and then you want to um, yeah, you want to take time derivative, you use j omega dot and then plus omega cross this vector. It's same as here, but I should switch, right? I switch this one to here, okay. Then you can see the same thing as here, okay, because this one actually is from dh over dt like this, okay. Okay, yeah, so you know why this term appear, why not just j omega dot? All right, so why are these equation important? Okay, why? Okay, let me summarize what I have. All this equation. So first, inverse kinematic. We have phi dot equal to j times h v dot, and we have, well, hb dot equal to r transpose h dot, right? And we have relationship between acceleration, this one equal to r times hb dot and then plus omega cross h dot, okay. Then I can write h, oh sorry, this one hb double dot, hb double dot equal to r inverse r transpose of h double dot minus omega cross h dot, right? Okay, so why are these equation important? Okay, this one and this one are important, okay. This one and this one. So when we want to control a robot to move along a trajectory, we need the information of the trajectory itself, right? So the idea from here, okay, let's say uh, for the actuator part, control engineer can control velocity of all actuator. Okay, let's say, well, I use DC motor or I use brushless motor or whatever, but I know how to control the velocity of those actuator. Okay, it means, okay, they know how to build a control system. Uh, so they have controller here, okay, and to their system and so on. So I don't need to care, right? And also for that control, they also need information of acceleration. Okay, first, let me state it clear here. So they can control velocity, which means as long as we give the desired velocity, then the feedback control system ensure that you can have velocity here, the actual velocity approach to desired velocity, which means the error here is go to zero. Okay, error phi dot here is tend to zero. But at the same time, for some control architecture, not only did they need, not only do they need velocity information, but also acceleration. Let's say also need acceleration. Um, well, so let's say here it may also need acceleration from here. Okay, and do some compensation to here, right? Okay, let's dot here. Well, so where can I get phi d dot the velocity of the motor? Of course, it's from the trajectory of the robot that we want the robot to move. So we have relationship of this one with this one with HB here. Okay, so we need inverse kinematic here. Inverse kinematic that the input must be HB so that we can have phi B here, right? Oh, I forget to give another equation actually. What about phi d double dot? What can I have here? Because J is constant, then I can have HB double dot like this. So to have phi d dot here, or phi d double dot here, I need also the inverse kinematic, but for acceleration, okay? Inverse kinematic for acceleration, this one inverse kinematic for velocity, okay? So it means I need to input HB double dot here. This one, oh sorry, this one is HB, H dot B. And then question is that how can you get HB dot and HB double dot? You need to plan the trajectory in the global frame here. You need to plan the trajectory. You need to give the information of velocity and acceleration in the global frame. So you use all this kind of transformation. You can compute this one and this one. So the thing is, well, first you need to have H double dot. Then you can just integrate it. You can, well, you just integrate it. You have H dot, right? Okay, so from H double dot and H dot, so you use this equation or transpose H double dot minus, well, I just maybe I just draw like this. So these terms will be inside here. Okay. And then here you get HB double dot. So from HB double dot, use inverse kinematic, you can have phi d double dot. Okay. And from H dot here, you use inverse kinematic as well. And then you have phi d dot. Okay. And then for this desired acceleration and um, velocity, you can use for the control for the feedback control at the actuator. Okay. There's one point that might confuse you. That is about rotation matrix, because is rotation matrix itself is function of h. H means, but actually that only psi, but psi is the last component of h. So where you get that psi? Okay. So actually, in order to get h, okay, in order to get h, you need to integrate this one, then you get h, and inside h, you can you can split the third component, which is psi, and then so this one is called, yep, the psi. You also need to use in here. Okay, just connect to here. Okay, let's say this is just a terminator. Okay, psi is used here. Where can you use it? Also in here, because this also inverse kinematic that has rotation matrix. Wherever you have rotation matrix, you need psi. So this psi also put in here. Okay. So all of these kinematics, inverse kinematics, are useful on the part of uh, trajectory generation for to generate the desired velocity, desired acceleration for actuator. Okay. You have any question? Any question, Luca? Anyone? All is clear from here, because H has H, Y, and psi like this. So we take the third element, only just the third element, in order to build a rotation matrix. Okay. So if you don't have question, you can have a break up for 5 minutes. Then we will restart at 7 past 10.